Hello, this is Darren Pulsipher, Chief Solution Architect of Public Sector at Intel, and welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. On today's episode, we're going to talk about destroying storage tiers with Randy Hayes from Vast Data.
Hey, Darren, thanks for having me on.
Hey, Randy, thanks for coming. We've done some work together over the last 3 or 4 months. It's been a lot of fun. I said, we got to get Randy on because you guys are doing some incredible things in storage right now.
Yeah, it's been a lot of fun, and this company is an absolute rocket ship right now. So, I've been on board at Vast a little over 2.5 years, really before we even had a product. And it's been a lot of fun. And so, going through the Series C funding, we just got another $100 million, bumped up our valuation to $1.2 billion. And, we're the fastest storage company to ever reach quote unquote unicorn status, with the revenues that we've done. So
what's all the hype? Come on. There's unicorns all over the place, but with storage, come on, storage is old.
Yeah, no, it is. And, candidly, I've been, working with the federal government for probably close to 20 years now. And so it's been an interesting ride. I mean, I really cut my teeth, early on at a company called Isilon. They did kind of scale out NAS. It was great. It was easy to use, easy to set up, but, we always struggled with performance and scalability. And so, I did a couple of years there, and then I went to a company called Data Direct Networks, and, we did GPFS and Luster, and it was super fast, and it scaled really big, but it was really hard to manage. And so it was like, all right, I traded, I had a trade-off. I gave up the easy to, manage for really fast and really big. And then kind of, after DDN, kind of the cloud was hot. And so I went to a company called Avere, and I spent 4 years at Avere. It was a hybrid NAS, hybrid cloud technology. And, it was interesting with Avere because they had this, flash cache, and it was always trying to cache data. And it was really tricky to cache a random read. And then, I end up at Vast, and, Vast is kind of a culmination of all the trade-offs that all those other companies had into one product. And so, the real thought process around Vast was, if you can build a storage system that's as fast as your fastest tier, right? Like a parallel file system, but as cheap as your cheapest tier, and, and you can build the storage system on, that has the fast tier and, the low cost perspective of this, it gives you the ability to compress everything down into a single monolithic storage system that can handle all your workloads. And so now it's easy to use, and it's as fast as the fastest file systems out there.
So you decrease all that complexity that we normally have in multi-tiered storage solutions, where you need a team of storage architects, right? And policies and automation, and you guys are doing that all in one bundle.
Yeah, 100%. And I think the other thing to remember and think about is not only like you have all these tiers, but, the government loves, competition. So a lot of times you have multiple vendors at every one of these tiers, right? And so now you have admins that are like, all right, I got to learn this, and I got to learn this, and then I got to learn this. And even if it's from the same company, right? Like the big storage companies, they're not really innovating. They just buy new products. So you end up, even if you bought it from one place, it's all different file systems and it's all different architectures.
What a nightmare. All right. So take us through you gave us the history, you gave us why Vast Data. Take us through how this thing works.
Yeah. So, we took advantage of 3 technologies that really didn't exist before 2018. And so we looked at, storage, from a clean slate perspective, right? And so our founder, Renan Halleck, came from Extreme.io. And when he was out at Extreme.io, he was running around trying to sell more flash. And what he found was users didn't really need any more performance from all that flash, but they needed to support file and object and be an order of magnitude cheaper. And so by taking a clean slate and listening to all the customers, we started building a technology around these 3 technologies that really weren't generally available until 2018. And so We use NVMe over fabrics. A lot of people think about NVMe over fabrics as like this really fast host side connection. We don't use it like that at all. If anything, we use it as kind of a hyper scale SAN to kind of connect everything together with really low latency. We use QLC Flash, which is great. There's, QLC Flash is very inexpensive. There's no moving parts like hard drives, and it's very, the read performance is fantastic. The write performance is okay. And these things don't last very long, right? You can't overwrite them, lots and lots of times in some sort of production environment. And then the last piece of the technology that we use is something that I'm sure, all too well, and that's 3D XPoint and Optane, right? And so you can think of it as we take the least expensive flash we can get our hands on and we wrap it with the, I don't want to say the most expensive flash you can get your hands on. It's not that expensive, right?
No, it's not.
But I think the thing that we love about, Optane is the fact that it's persistent. And so now we can get rid of all the DRAM in the write path of our storage system. And if you think about, and if you talk to anybody that's worked in either storage engineering or, storage support, most of the time when you have some sort of failure or you have some sort of data loss event, it's from destaging from DRAM down to flash, whether there's a failure from a controller perspective or a failure from power or something like that. And so the fact that we have no batteries and the fact that Optane is completely persistent when you write to it, it gives us a really great advantage with the architecture. And so wrapping these three technologies together gives us the ability to give you this, all flash performance, but it, allows us to drive the cost down into something that competes more with like the hard drive.
That's pretty incredible when you think about it. So what you guys have done is eliminated the need for those other tiers that we were buying in the past because they were cheap.
Yeah, 100%, 100%. One of the things that, to think about how this architecture is laid out is we've built the first disaggregated shared everything architecture. And so really what that means is we disaggregated the logic from the state of the file system. And so the state of the file system lives in these, what we call D boxes or data boxes. And that's where we have all this QLC Flash and we have all this Optane. And so we use the Optane as a big distributed write buffer. And we also use the Optane as a really big metadata store. So it's kind of a multi-use, just like our system, we brand as universal storage. We use Optane for all kinds of things inside of the storage fabric. And so you have these boxes, there's no single point of failure, so you can start with as little as one. And then you can grow the capacity to really as big as you want. And so that's where the state of the file system lives. On top of that, we have where the logic of the file system lives. And we write all of our software in Docker. And the fact that we write all these things in containers makes it very easy to deploy and very easy to iterate on the file system. So we've been able to crank out a tremendous amount of features very quickly with this storage architecture. And so that's where the disaggregated piece comes in. So the logic runs in these x86 servers that we source, because nobody really wants to mess around with Docker and containers and that sort of stuff. People want appliances. People want easy to use. So we provide these x86 servers that run these Docker containers, and that's where the logic of the file system lives. And so you can now grow capacity by just adding these data boxes, and you can add performance by just adding these inexpensive x86 servers into the cluster. And
now,
so,
when you first described this to me, I said BS. That's the first thing I said was, I don't believe it, because I've done file system design and all this stuff, and you're telling me I can grow this to how big?
Well, I'll give you.
You said indefinitely, but come on.
Theoretical, right? There's the theoretical limit is unlimited, right? But from a testing perspective, we've tested. Let's see, what are we at? About 50 petabytes now is what the testing limitation's been. So
all in one file system.
All in a single file system, correct.
Wow.
And
But
so
theoretically, I mean, you guys explained your algorithm to me. Theoretically, it can go on forever. That's
it's,
all pretty awesome.
it's an embarrassingly parallel file system. And so that's actually one of the big points that I was going to make with the disaggregated shared everything architecture. The reason it can scale so wide is because of the shared everything. So, we talked about these containers that are running on these servers. You have clients that connect to these servers, and then any server that's running our software, these Docker containers, has equal access to every single piece of media in all of these boxes, like it's direct attached. So NVMe over Fabrics gives you 5 microseconds of latency between those servers and the media sitting down in those boxes, whether it's 3D Crosspoint with Optane or QLC Flash. And so because any user can access any piece of data from any one of these servers, it gives us the ability just to continue to scale and scale and scale. And these boxes are stateless. So they can come and go. You can grow them. You can expand them. You can grow the cluster. You can shrink the cluster on the fly, depending on what your requirements are.
All right, so capacity, I can see that. I can grow indefinitely. What about performance? Am I going to take a performance hit the more nodes I add? It sounds like I might.
So as you add nodes, you're just focusing on capacity, right? And so capacity. And then because Flash is really built for lots and lots of concurrency, the only thing that's inhibiting the performance of the Flash is the CPU. And so by giving you the ability to seamlessly scale the number of CPUs in the cluster, it gives you the ability to grow your performance really at will, right? And you're just adding these, cheap x86 servers into the system that are running Linux, right? It's just, there's nothing special about these servers. And so, you're adding these servers and you're just adding more performance to the system, as you continue to scale the cluster.
So you're telling me I can scale performance independent of capacity.
Yep, absolutely.
That's pretty darn impressive.
It's really neat because I'll tell you where I think one of the problems that we've really solved is the latency problem, right? And so a lot of our customers just want lots and lots of capacity, and they don't need just all out performance. Some of our customers do, but a lot of our customers just need really low latency to all of their data. And so because, you have these stateless protocol servers have access to everything, regardless of which one of these servers you connect to, you have really fast access to all of the data. And so we have, customers that have, let's say, 6 of these vast servers and 20 of these vast, data boxes, right? And so they have lots and lots of capacity, and they're just focused on low latency versus just all out bandwidth or all out IOPS.
Really, this is really fascinating because I can fine tune my storage pretty easily, it sounds like.
Yeah.
Right?
Yeah, no. And I think one of the really cool things, I've been doing storage for a long time, and you're always, in a room with somebody and you're whiteboarding and you're trying to figure out what problems that they're dealing with. And, the composable nature of these stateless protocol servers gives us a lot of really cool things to whiteboard out and show customers how to do this. And because the servers, there's no crosstalk between all these servers. It's all north-south traffic. There's no really east-west traffic. It gives us the ability to break these things into pools. And it gives us the ability to kind of have this, what we like to call brute force quality of service. So you can, layer on the virtual IP addresses to just some number of these servers for, let's say, a batch compute cluster. And then you could have some number of servers that are pinned to, let's say, your head node or something like that for interactive use. Or if it's an AI workload, you have an ingest, pool where you're just bringing in data. And then you have kind of a read or egress pool, right? And so it gives you the ability to kind of build the cluster however you would like.
So with this, I can segment off my control boxes, right? The client boxes, right?
Yep.
I can segment those off based off of different workloads, but they can all still access the same data, correct?
Right. Yep.
That is really, really slick. where now my storage can be fine-tuned based off the applications, but not really the storage, just the access to the storage.
Customer that we've been working with, and they initially put out this requirement for like 3 tiers of storage, and we're like, yeah, no, you don't want to do all this tiering, like it just it's kind of a nightmare. And so they were talking to a couple different companies, and and people are building out all these different tiers, and we're like, well, we're just going to give you a single file system. And they're like, no, just you need to give us 3 different tiers. And we're like, all right, well, it's all the same stuff, right? So it's like, we have like this one, section that has, some number of data boxes, and then another tier that has the same number of data boxes, and another tier that has the same. And I'm like, your tier 3 now has the same performance as your tier 1. Let's just combine all this together. And they're like, yeah, that's probably what. But for the RFP, you had to give us 3 different tiers. And I was like, okay, but like in real practice, you really want to compress this all together into a single tier. Or if you have a DR requirement, we do have the capability to punch data off into S3, whether it's into the cloud or, another vast system, or to, something inexpensive like Ceph or, another, low cost object storage system. And so, if you have that need for a secondary site or something like that, we can support kind of the replication thought process of like, hey, if this site becomes a smoking hole or flooded or whatever it might be, your data's somewhere else, right?
Gotcha. Now, another thing, we worked on a customer together, and they had a requirement for some data at different classification layers than other data, and you showed a brilliant way of actually segmenting off the data as well, and having different restrictions around access to data and things using the same infrastructure. I thought this was pretty brilliant. Well, you want to describe that a little bit?
Yeah, no, absolutely. So with the same, general thought process of, carving out with the C nodes and, giving you the ability to have multiple access zones and multiple, virtual IP pools, you have the ability to segregate what users have access to which one of these, CBOX pools, if you will, via virtual IP addresses. And so some users can only see data, from here. It's one of the challenges with NFS, right? NFS broadcasts to basically everything, right? But if you limit, where NFS actually broadcasts to a subset of IP addresses, it gives you the ability to kind of carve out those different architectures into, kind of discrete systems where people can't step on each other and really won't be able to see certain exports that are in maybe a program that they don't have access to or something like that.
Very cool. Now, I've also thought about using this same idea to actually create different environments in my vast data system for development, test, and full production. I could easily do that because there's different performance and access capabilities at each one of those, but still using all the same storage. It's pretty brilliant.
Yeah, it's funny. We have a university, and so like the system starts at 600 terabytes, right? So it's like we don't do small. It's just we're typically talking about petabyte or larger opportunities, and so the university was like, you don't need a petabyte just for HPC. Like we just need some scratch space. We need maybe a couple hundred terabytes, and they're like, but we have this backup requirement where we do need lots and lots of storage. And so we have a university that literally uses us for HPC scratch and as a backup target.
Oh, that's hilarious.
Like, so it gives you kind of the breadth of like the fastest of the fast and kind of the cheapest of the cheap from a backup perspective. And, it really can all be supported from this single universal storage system.
Very, very cool. So practicality on this. Let's talk about that. How you said you're a pretty young company still. Do you have any big wins? How can I trust you guys? Storage, that's everything to me, right? So do you have some good business cases already that you've already been able to prove out that, hey, this really does work?
Yeah, no, absolutely. So, From a federal government perspective, we're cranking out huge systems. We have multiple installs across multiple institutes inside of NIH. So we're at 4 different institutes inside of NIH now. Actually, a 5th is in procurement. So we're going to have 5 separate institutes. We're in a couple locations in NOAA. We have a couple of IC customers that probably don't want me talking about them on a podcast. We have a lot of Department of Energy. We're in all the tri-labs now. So, I think it's an interesting thought process when you start looking at, DOE and especially the tri-labs, because they're just, they're so focused on performance and, we need all out performance, for all these supercomputers. And like some of these places have like 30 different compute clusters. And in one of the locations, we're attached to all of them at the same time. And so it gives you an idea of how powerful this system can be and some of the largest, HPC environments in the world in supporting mission critical applications.
So what if I'm not an HPC cluster? I mean, is your solution only really geared towards HPC? Is it cost prohibitive that way? Because HPC, those guys have a lot of money, right?
They have a lot of money, but they are super cheap. They are the cheapest of the cheap. And they want the cheapest storage because, and I look at it as, a lot of the places that we're in are places that either have impossible missions, right? In the intelligence community where you have the needle in the haystack problem, right? It's like, we're trying to find something, we don't know what, but we're trying to find it. And, so we end up really good in those those type of situations. The other ones are, places that are doing research, around, let's say, cancer or COVID seems to be something that people are talking about once in a while lately. And so, we're doing a lot of different workloads around COVID, whether it's next-gen sequencing or it's confocal microscopy and cryo-EM. We're doing a lot of financial hedge funds, back testing, things like that. And, as much as like selling backup, appliances is really boring. I really like, kind of the COVID stuff and, the life sciences workloads. But, as far as a backup appliance, like that's kind of like the lowest risk place that you can kind of put storage. And so, a lot of people are like, yeah, we don't trust you quite yet. We're going to put you in backup. And so I got a great kind of ad lib on this. So we have a customer at National Cancer Institute that they're looking to replace a tape library. And, they were using this tape library as an active archive and they wanted to, use it for some, they needed something that was a little bit faster than tape for this active archive. So they started looking at all these different platforms. They were looking at Isilon and Cohesity and Pure and all these other things. And we came into them and we gave them a price point that was lower than everybody's price point for all flash. And so now they have this all flash active archive that is faster than their production NAS system. And so, it just, and that's just general file sharing. It's not high performance computing. It's just, hey, we need, this big active archive and, we want good performance, but, the price point was correct.
So, I mean, your solution has a good price point. It's geared towards general, just file sharing, not just geared towards HPC. It is a killer product. I love the collapse. I love how you collapse the tiers. It's simple to use, simple to manage. I think you guys really have something cool here.
No, I appreciate it. It's been a whirlwind, and we've been really taking the storage industry by storm. It's been a lot of fun, and you start looking at other workloads. Whether it's like AI seems to be kind of hot right now. Everybody's talking about AI. And I think the big challenge with AI is, it was very easy back in the day, right? When humans were reading the data. It's like, all right, this data is hot, this data is warm, this data is cold. It was easy to tier. But now when machines are reading the data, they want fast access to everything, right? And so you can't cache a random read. And, that's one of the biggest challenges with how everybody's trying to solve this problem with hard drives is, we'll put some sort of like, fast cache in front of the hard drives, but you can't cache a random read, and AI is all random reads. And so it's a killer use case for that. We're doing a lot of stuff with Splunk and log analytics. whether it's Splunk or Elastic. There's a lot of really cool workloads like that. I mean, I think, looking at backups, looking at log analytics, looking at AI, looking at HPC file store, I mean, it's universal sources.
Thanks for listening to Embracing Digital Transformation today. If you liked our episode, go ahead and give us 5 stars on your favorite podcast or video streaming site. You can also find out more on embracingdigital.com. Until next time, keep moving forward and embrace the digital revolution.